In this video, we will look at a few more applications of Gauss's law. We are going to use Gauss's law to calculate the electric field produced by an infinitely long thin wire of charge. Now, we have done this problem using Coulomb's law. And let me just quickly remind you how we did this problem using Coulomb's law. What we did was we first started with a finite wire, right? And we put the wire on the y-axis symmetrically. And then we took a tiny element of charge on the wire, called that dq. We calculated the electric field produced by dq at the point of interest, which I think we called that capital R when we did this problem. So the electric field would have been dE, right? We broke up the dE into two components, dE sub x, dE sub y. And we noticed that the dE sub y's would cancel out because we placed the wire symmetrically. So we didn't have to integrate over dE sub y, but we did integrate over dE sub x to get the net electric field at the point P. And that's how we found the electric field. And then for an infinite wire, we took the limit that the length of the wire was 2a. We took the limit that a tends to infinity. And once we did that, we got the result that E is equal to lambda over 2 pi epsilon 0 r. So this is the result that we got after a tremendous amount of work. Now we're going to do the same problem using Gauss's law, and let's see how that's going to work. So we have the wire, and it's an infinitely long wire. The charge density on this wire is lambda. Okay, now if the wire is infinitely long, then this particular charge distribution, what kind of symmetry does it have? The charge is uniformly distributed on the wire and the wire is infinitely long. So what kind of symmetry does it have? The correct answer is that this has cylindrical symmetry. Why cylindrical symmetry? Just imagine that this pen is the wire, and just imagine that it's infinitely long, right? It's very, very, very long, so that you can't see either end of it. Okay, now if I just turn this wire if I just twirl it so that I'm rotating it about the axis which passes through its center, about its central axis, you cannot tell that anything is changing with this wire, right? So a long wire has cylindrical symmetry, the same symmetry as a long featureless cylinder. If I rotate it about any other axis, immediately you can tell that it's been rotated. But if I just twirl it around, which means that I'm rotating it about the axis which passes through its center, you cannot tell that it's being rotated. So this has cylindrical symmetry. And so if the charge distribution has cylindrical symmetry, the field lines which emanate from this charge distribution also have cylindrical symmetry. Now, to understand what kind of field lines those would be, let's imagine an edge-on view of the wire. So let's say that the wire is coming out of the page right here. So this dot indicates that the wire is coming out of the page. And just imagine that the wire is infinitely long, and so it goes into the page infinitely far away. And we have this edge-on view of the wire. What kind of field lines could be coming out of this wire so as to not spoil the cylindrical symmetry? So clearly, if the wire is just giving off some field lines like this, that's all. These are the only field lines that are coming out of the wire. Then it would spoil the cylindrical symmetry, because if you rotate the wire a little bit, then the whole pattern of field lines will shift like that, and you can tell that it's been rotated. So this is not cylindrically symmetric. Just a bunch of field lines coming out in one way and not other ways is not cylindrically symmetric, right? So what would be a cylindrically symmetric pattern of field lines coming out of this wire? Well, how about if the field lines are all in the radially outward direction? Would that be cylindrically symmetric? The answer is yes. If the field lines from the wire are all coming out in the radially outward direction, like this, my finger is now pointing towards the field lines, then that would be cylindrically symmetric, right? Because if you were to twirl this, if you were to rotate this wire about its own axis, then the field lines nothing would change with the field lines. And so that would be cylindrically symmetric. So that tells us that the field lines will be radially outwards or inwards. So cylindrical symmetry implies that field lines are radially outwards or inwards. Can you tell me whether it's outward or inward? Since we are told that the wire has positive charge, that's given in the problem, we know right away that the field lines are radially outwards, not inwards. If the wire had negative charge, the field lines would be radially inwards. Now, I'll just make one comment here. We deduce that the pattern of field lines is radially outwards because that's the only pattern that we can think of that has cylindrical symmetry. However, is that true? Is that the only pattern that has cylindrical symmetry? Pause the video for a moment and see if you can think of any other pattern of field lines which would have cylindrical symmetry. Okay, how about this pattern of field lines? So here is the wire, right? Suppose the field lines form closed concentric circles like this. And maybe they're going. Would this have cylindrical symmetry? The answer is yes. This is also a pattern of field lines that is consistent with cylindrical symmetry. However, would this particular pattern of field lines make sense in this case? The answer is no, because you know that electric field lines, at least the ones we are seeing now, they always originate from positive charges and terminate on negative charges, right? Or they just go out to infinity. So they either go out to infinity or they terminate on negative charges. These field lines don't originate or terminate on any charges at all, the blue ones. And that is why they don't make sense in this as field lines coming out of the wire. So on those grounds, we disregard this particular pattern of field lines, even though it is consistent with the symmetry. And so we are only left with one possibility, which is the field lines are radially inwards or outwards. Okay. We will see later on that this second pattern plays a very important role, but that would get us too far ahead in the story. Okay, so for now, what we can see is that the field lines are radially outwards, right? So we can write down the electric field as a vector. So the electric field would be cylindrically symmetric. So E would be some function E of R. And this E of R would be fixed at a particular R. So E of R only depends on R. And at a given R, E is going to be fixed. And we are going to have the unit vector R hat. So it has the same form as for spherical symmetry, except that we are now talking about cylindrical symmetry. Okay, so E is equal to E of R, R hat. So please make sure you understand what this means. This tells you that the magnitude of the electric field only depends on the radius R. So if you're at a given R, if you're at a given distance, whether you're here or whether you're here at the same distance from the wire, you have exactly the same magnitude of electric field. The direction of the electric field would be radially outwards. So over here, the electric field would be in this radially outward direction. And over here, the electric field would be in this radially outward direction. The magnitude would be the same. Okay, so that's what this mathematical statement is saying very concisely. Okay, so that's our electric field. And so we've determined that this is a case of cylindrical symmetry. So now it's time to think about what kind of Gaussian surface we're going to use. So a good Gaussian surface to use, since the problem has cylindrical symmetry, is to just consider a cylinder. So let's consider a cylinder which has the same axis as the wire, a short cylinder like this. That is our Gaussian surface, right? A short cylinder which surrounds the wire. And let's say that the length of the cylinder is L. And let's say that the area of each flat face is A. So each flat face has an area A. Actually, since I was always using a different color for the Gaussian surface, so let me just do that. There. So this blue cylinder that I just drew is my Gaussian surface, and it has the same axis as the wire. Right? So that's my Gaussian surface. And the length of the cylinder is L. The area of either face, either flat face, is A. Okay, so we have to find, let's write down Gauss's law for this Gaussian surface. Gauss's law says that the total flux over the Gaussian surface, which you can also write as the surface integral of the electric field over the entire Gaussian surface, these two mean exactly the same thing, is equal to Q enclosed divided by epsilon 0, right? Okay, so let's see if we can figure out this surface integral, right? The electric field is cylindrically symmetric, which means that the electric field lines are all radially outwards. What is the flux of the electric field over, let's say, the top surface? Right? So the top surface, you can see right here in the diagram, what is the flux of the electric field over this top surface? So to answer this question, think about how the field lines are arranged over the top surface. So they're all radially outwards. I've drawn a few field lines for you. So can you tell me what is the flux of the electric field over the top surface? The answer is 0. And that is because the field lines are all skimming the top surface. None of the field lines are penetrating the top surface, right? So the flux over, let's call this surface 1. Top surface is surface 1. The curved surface is surface 2. And the bottom surface is surface 3. So the flux over surface 1 is going to be 0 because none of the field lines are cutting that surface, right? Okay, surface 1. All right, what about the flux over the bottom surface? It's exactly the same thing. The field lines are all skimming the bottom surface, and I can also draw a couple for you. Notice that the field lines are all just skimming this bottom surface since they're radially outwards. So for the same exact reason, the total flux over the bottom surface is 0 for exactly the same reason. So there is no flux over the top surface, no flux over the bottom surface. And just to remind you, flux simply counts how many field lines are cutting the surface, the net number of field lines cutting the surface. So there is no field lines cutting either the top surface or the bottom surface. So there's no flux over them. So we now just need to calculate the flux over the curved surface of the cylinder, right? So this we are going to do in a manner that is very, very similar to what we did in the case of the spherical symmetry. So let me just draw another diagram here since the other one is getting pretty cluttered. So here is the wire. Here is my Gaussian surface. And the field lines are all radially outward. So I'll draw a couple. So I've just drawn 2 field lines which are radially outwards. So I want to find the flux of the electric field over this curved surface, right? And I've chosen, obviously, I've chosen the cylinder to pass through the point where I want to find the electric field. So I'm interested in finding the electric field at a point P. So I've chosen a cylinder which passes through the point P. So this is where at the point P is where I want to find the electric field. Okay, out at distance R. So let's say that the electric field on the surface of the cylinder at radius R is given by the unknown function E of R, right? So the electric field vector is going to be E of R times R hat, right? Let's choose a tiny little dA on the surface. So when you take a surface integral, you break up the surface into tiny segments and you calculate the flux over each segment by doing a dot product with the electric field, and then you add up all the segments to get the total flux, right? So that is the surface integral, and that's what we need to do. So E is this, dA, let's choose a tiny little dA. So we can choose it anywhere. So I'll just draw one over here. This dA is a tiny, tiny little patch on the surface of the cylinder, right? So what is the direction of the normal to dA? It will be in the radially outward direction. So it will be exactly the same direction as the electric field, which is also radially outwards, right? So dA would just be dA multiplied by r hat. Notice how similar this is to the spherical symmetry case. So now you can just follow exactly the same steps that we had in the case of spherical symmetry. The next thing to do would be to calculate E dot dA. So that is going to be our unknown E of r multiplied by dA. Okay, then we have to integrate this over the entire surface of the cylinder. So we have to calculate E dA, surface integral E dA. We only need to do that over the curved surface because we've already figured out the flux on the top and the bottom surfaces. So this is only over the surface 2, right? So that would be surface integral E of r times dA, right, over the surface 2, which is the curved surface. Now, E of r, will that be a constant? So on the surface that we are considering, the radius is fixed, right? So the radius is fixed at r, which means that we can simply treat the r as a constant because it's fixed. We are considering a cylindrical surface. So the radius is fixed. So that means E of r is a constant, and I can just pull it out of the integration. So E of r, surface integral dA, is what we have, right? Now, we know how to figure out the meaning of surface integral dA. Surface integral dA would mean it is simply the sum of all these little patches of area that are on the cylinder, curved surface of the cylinder. So if you do surface integral of dA, this is nothing but, this will just give you the total curved surface or total area of the curved surface, which is number 2, surface 2. And what is the area of the curved surface of a cylinder? It's 2 pi r multiplied by L. So length is L. The area of the curved surface of a cylinder is 2 pi RL. So that's, so the surface integral just becomes E of r times 2 pi RL. And just like in this case of spherical symmetry, if you're integrating over the surface of a cylinder, you can, if you want, you can just jump straight from here to here. The surface integral of a field over, when you have spherical symmetry, the surface integral of an electric field over, sorry, when you have cylindrical symmetry, the surface integral of an electric field over a cylindrical surface is just E of r times 2 pi RL. Okay, and so that is the flux over the curved surface. So this is the flux over surface 2. So we found the flux over the two flat surfaces, they were both 0, and the flux over the curved surface comes to E of r times 2 pi RL. So the total flux over the Gaussian surface would simply be the flux over the two flat surfaces plus the flux over the curved surface. So that is just going to be E of r multiplied by 2 pi RL. And this should equal the total amount of charge enclosed inside the cylinder. Now, let's figure out how much charge there is inside the cylinder. So the total amount of charge, the charge density on this wire is lambda, right? The cylinder only covers a length L. That's the length of the cylinder. The cylinder only encompasses a length L of the wire, right? So how much charge is inside the cylinder? Can you answer that question? So if the cylinder only covers a length L, how much charge is inside the cylinder? The answer is going to be lambda multiplied by L. So the Q enclosed will simply be lambda multiplied by L. And just to repeat myself, here is our cylinder and its length is L, right? The wire, I'm just going to draw the wire with a different color just to make this clear. The wire is like this. The cylinder is only covering a length L of the wire, of this infinite wire. It's only covering the length L. So the amount of charge that's contained in the cylinder is just the amount of charge that's over a length L of the wire. And so that's going to be lambda multiplied by L. So I need to divide this by epsilon 0 to get for Gauss's law, right? So we are done. So now the electric field at a distance r from the wire, E of r, is going to be, if you set these equal and solve for E, it's just going to be the L cancels out, lambda divided by 2 pi epsilon 0 r. And so you can see how ridiculously easy this was. We didn't have to do any complicated integrals or anything like that, breaking stuff up into components. We got the answer with one very trivial calculation. So this also shows you the power of Gauss's law. And this is an example of applying Gauss's law in a situation where you have cylindrical symmetry. We're going to look at one more example of Gauss's law. So we're going to use Gauss's law to find the electric field that's produced by a flat infinite sheet of charge. Let's say that the charge density on that infinite sheet is sigma. Okay, so we've also done this problem, or had kind of done it in using Coulomb's law. And in fact, we skipped the details of the calculation when it was there in the chapter 21 PowerPoint, but we didn't quite do it because I told you that it's rather complicated. So we actually skipped the details of the calculation, but I did show you how you can take a finite disk of charge and then you find its electric field using Coulomb's law. And then you turn that finite disk of charge into a plane by taking the limit that its radius is infinite. So then the disk becomes a plane. And so I showed you that part, taking the limit where the radius becomes infinite. And we got the result that the electric field was sigma divided by 2 epsilon 0. It doesn't show up on my iPad for some reason. So this is the result that we got from Coulomb's law, and it was pretty complicated. Getting this result from Coulomb's law was pretty complicated. We're going to do the same thing with Gauss's law and just watch how incredibly simple it is with Gauss's law. So what we're going to do is that we're first going to consider what kind of symmetry this problem has. So we have an infinite sheet of charge, right? So this obviously has planar symmetry, and planar symmetry means that if you close your eyes, you're looking down at an infinite sheet of charge. If you close your eyes and your friend moves that sheet a little bit, you open your eyes, will you be able to tell that the sheet has been shifted? The answer is no, and that is an example of planar symmetry, right? So if the charge distribution has planar symmetry, that means the electric field produced by that charge distribution should also have planar symmetry, right? So what kind of field lines would have planar symmetry that way? If you think a little bit, you'll realize that the only possibility is if the field lines are all perpendicular to the sheet everywhere. So they're coming out of both sides of the sheet in both directions, and they're everywhere perpendicular to the sheet. So if this is the sheet, then the electric field lines will all be either coming out of the sheet this way, or they'll be coming out of the sheet this way. So you would have uniform electric field lines coming out of the sheet, either going up or going down. So that is the only way the field lines can also have that planar symmetry. If the field lines had any other distribution, then that would not be consistent with planar symmetry. So from the planar symmetry, let me just copy this diagram over here because it's a nice one. Okay, so from the planar symmetry, we know that the electric field lines are perpendicular to the to the sheet in both directions. So the electric field lines, if this is the sheet, the electric field lines would be coming out of the sheet like this and also going the opposite way, both sides of the sheet. And so what is a good Gaussian surface that we could use? So a good Gaussian surface that we could use is simply a little cylinder which straddles the sheet. So consider this imaginary cylinder, which is indicated by in purple over here, which is straddling the sheet. So it's one part of the cylinder is on one side and the other half of the cylinder is on the other side of the sheet. So Gauss's law says that the flux of the electric field over the Gaussian surface is equal to the charge enclosed by the Gaussian surface divided by epsilon 0, right? So this cylinder has three faces, right? So there are two flat faces. Let's call these faces 1, 2, and 3 like before. This is face 1, this is face 2, and the curved face, this is face 3, and the curved face is face 2, just like before. So we have to find the flux over face 1, the flux over face 2, and the flux over face 3. That would be the total flux over the Gaussian surface, and set that equal to Q enclosed divided by epsilon 0. Okay, now what is the flux over the curved surface? Let's do that one first. Notice that the field lines are all perpendicular to the sheet, which means that they are all skimming the curved surface. None of them are penetrating the curved surface. So please pause the video and make sure that you agree with that. The field lines are all perpendicular to the sheet, so that means they're all skimming the curved surface of the cylinder. So they're all going like this. So none of those field lines, the yellow lines that I drew are the field lines, some of the field lines coming out of the sheet. None of the field lines are penetrating the curved surface, which means that the flux over the curved surface is just going to be 0 in this case. So there is no flux over the curved surface. What about the flux over the flat surfaces? Now, what we can conclude from the planar symmetry is that the electric field at a given distance from the sheet has to at most depend just on the distance from the sheet. So if this is my sheet, if this is the sheet, and I'm considering the electric field at this distance from the sheet, then the electric field at the same distance over here must have the same exact magnitude as the electric field over here, right? Otherwise, the planar symmetry would be spoiled. If the electric field over here was very, very strong, whereas the electric field just a short distance away has a different magnitude, then if this whole arrangement were to be moved to one side, you would be able to tell that it's been moved, right? So that tells you that for planar symmetry to hold, the electric field at a given distance from the sheet has to be constant in magnitude. Okay. So the electric field is going to be perpendicular to the sheet, right? And it will have the same magnitude at every point on surface 1, right? So it looks like we can calculate the flux without actually doing a surface integral. We are good to use the simple formula for the flux, which states that flux is equal to, the simple formula states that flux is equal to E dot A. And remember, this only holds when E is constant over A, which it is in this case for planar symmetry to hold. And the second is when, second condition is that A is flat, which it is, because the two flat surfaces of the cylinder are what we are considering. So we can just use the simple formula for flux. So the flux over surface 1 would just be the unknown value of the electric field multiplied by the area of the flat surface. Let's call that A. It's going to be E times A times cosine of the angle between E and A. What is the angle between E and A for surface 1? So E is pointed away from the sheet. So this is the direction of E, away from the sheet. And the area also has a direction away from the sheet because you have to take the outward directed normal. And so the angle between E and A is 0 and cosine 0 is 1. And that is why this is equal to E multiplied by A. Okay. All right. Now let's move on to face number 3. So here the electric field is pointed away from the sheet on the other side. And the normal to the area, so I'll draw a few arrows for the electric field here as well. And the normal to the area is also away from the sheet, right? So the electric field and the area have the same direction. And so it's again going to be E multiplied by A multiplied by cosine of 0 again. So that's E times A. And so the flux over phase 3 is going to be E times A. The flux over phase 1 is going to be E times A as well. And the flux over phase 2 is just going to be 0 as we had seen earlier. So the total flux is just going to be 2 times E times A. And how much charge is included in our cylinder, the Gaussian surface? Again, the Gaussian surface only encompasses or only includes the area A of the sheet, right? So it only covers the area A, which is the area of one of its flat faces. That is the area of the sheet that's included in the Gaussian surface, right? So how much charge is in that area? Well, if the charge density is sigma, then an area A has a charge which is equal to sigma multiplied by A, and that is and then you have to divide that by epsilon 0. So the right side of Gauss's law just becomes, it's Q enclosed divided by epsilon 0. Q enclosed, which is the charge that's inside our Gaussian surface, inside this cylinder, is going to be sigma multiplied by A divided by epsilon 0. And so from here you can just immediately solve for E, and you get the answer. E is equal to sigma divided by 2 epsilon 0. Okay. Again, you can see how ridiculously easy it was to derive this result in comparison to the amount of work that you would have to do if you tried to use Coulomb's law to get this. Okay, so you can see how powerful Gauss's law is.